Thanks again, and thanks also to Gahad for inviting me to give a talk here. This is a very exciting conference. So in my talk, I will introduce a new interpretation of the wave functions in terms of the particle ontology. So this interpretation has been proposed and discussed in great detail in my recent book, The Meaning of the Wave Function in Search of the Ontology of Quantum Mechanics. So you can also download the final draft of the book from the archive. So although the idea may be new for most of you, but it had been with me for more than 20 years. The idea first came to my mind in 1993, about 1 year after the death of David Bohm. Then I was a postgraduate at the Chinese Academy of Sciences. So I had been very absorbed by Bohm's theory before I had my own idea. So I think Bohm's work inspired me to a large extent. So in this talk, I will not introduce the main argument in my book. Instead, I will discuss the idea in a broader context. Especially, I will compare it the idea with Bohm series and the collapse series. So in quantum mechanics, we have the Schrödinger equation, which governs the time evolution of a mathematical object, psi. The wave function assigned to a physical C-term. As many of you may know, the red picture is Annie and Schrödinger's grave site, or the name plate. The Schrödinger equations is inscribed. So the question is, what does psi really mean in physics? So this is a famous point written by Hooker and translated by Bloch. So when the Schrödinger equations were discovered, people was wondering what the wave function in the equations mean in physics. I think in order to know the true meaning of the wave functions, we had better begin what we know sure. This is Bohr's rule. The rule says that the modular square of the wave functions is probability. It represents probabilities for the results of measurements. So due to the appearance of probability, it seems very natural to assume the existence of a random process, which may be described by still unknown variables. I denote it with X. So no matter what the variables is, its time evolutions must depend on the psi, because otherwise we can't derive the Bohr's rule. Here I should note that the randomness here may be apparent or may be real, so corresponding to the time evolution being deterministic or stochastic. So we have X and psi in a psi-ontic theory. I think there are two well-known examples of such a theory, depending on which quantity represents the measurement result. The first one is Bohm theory, in which X represents the result, X as a particle configuration. The second example is collapse theories, in which the wave function psi represents the result. So here it's not only the result, it's actually the physical state on which our mental state supervenes on. So the question is how to understand X and psi in these two theories. Let us first say the Bohm theory. In Bohm theory, X is a particle configuration. It's in our three-dimensional space. It has no influences on psi. This is the first feature of the Bohm theory. The second is the psi influences X, but into distinct roles, into distinct ways. The first way is to give the initial probability distribution of X. The second way is to guiding the time evolution of X, which is deterministic in Bohm theory. So I think the existence of these two distinct roles of psi in Bohm theory seems not wholly satisfactory. The third is that X is in our three-dimensional space, but psi is defined in the 3n-dimensional space. So here appears the question, how can psi influences X? The last issue is that psi is defined in 3n space. This is an abstract space. So how to understand psi as a field, or a physical field in a high-dimensional space? So this is the features of the Bohm theories for understanding the X and the psi. So let's now turn to the collapse theories. In collapse theories, such as the GRW theories or CSL theories, first psi restricts the distribution of X. Here X is a noise, or a noise field or something like that, or flash. The second, X also has random influences on psi, which lead to the collapse of the wave function. So in collapse theories, X and psi has some interactions in some sense. But collapse theories also has its own potential problems. Some of them are very similar to the problems of Bohm theories. The third is X is in the three-dimensional space. The noise is in our three-dimensional space, but psi is in the 3n-dimensional space. So how can X influence psi? Why does X collapse psi? And where does the noise X comes from? And finally, why is the distribution of X related to psi, etc.? So the final issue is still how to understand psi, which is defined in a high-dimensional space. So I think a promising way to solving these problems is to unify the two ontologies, X and psi, into one ontology. I denoted psi X. So let me explain the meaning of the psi X. As I said before, in Bohm theory, psi has two distinct roles in influencing X. The first is through giving the initial probability distribution. The second is guiding the time evolution of the particles. So in my solutions, psi has only one role of determining the probability of X. So psi need not have two different rows. In my solution, psi has only one row, or just determining the probability of X. So the probability X is equal to the modular square of the psi X. So in collapse theory, psi restricts the probability distribution of X. So we have some questions which need to be answered. For example, where does the noise X come from? Where is the distribution X related to psi? So in my solutions, the modular square of the psi is just the probability distribution of X. So the same formula as last PPT. So let me quote John Bell here. Bell said in his 1990 paper against measurement, he said the wave functions gives not the density of stuff, but gave rather on squaring its modulus the density of probability. Probability of what exactly? Not of the electron being there, but of the electron being found there, if his position is measured. So why this aversion to being and the insistence on finding? So in my solutions, the psi X is about something is being, not only about something about finding. So according to my idea, the ontology of quantum mechanics is still particles, as in Bohr's theory. These particles are in our three-dimensional space, but they do not undergo the continuous motion. Rather, they undergo random discontinuous motion, RDM in brief. And psi is a property, or often call it a propensity property of these particles that determines their motion. So my idea is that psi has only one row to determine the probability of X. X here is still the particle configurations like in Bohr's theory. So here is an example. For example, for the electrons in a hydrogen atom, the electron is a particles in my theory. It undergoes random discontinuous motion in space. Then such motion is very quick, so it can form an effective electron cloud in the right picture. This cloud has mass density and charge density. And the density and the flux density can constitute the wave function of the electron. So this is a picture of motion for one particles. So here is we can also have a clear picture of motion of two entangled electrons or two entangled particles. So they move in exactly the simultaneous way. Then the state of motion of these two particles is described by wave functions, which will be naturally defined in a six-dimensional configuration space. So this is a picture. I think it may provide possible explanations for the quantum entanglement. But is this series just the Bohr's theory without trajectories? So Bohr proposed this for Bell proposed this Bohr's theory without trajectory in his 1981 paper. So Bell also called it the theory I've read question mark theory. I think although the bomb theory without trajectories can solve the measurement problem, as Bill argued in his paper, but this theory has some problems, such as the empirical incoherence problems and other problems. So I think it's not very satisfying. So I will propose a new theory. So it's bomb theory without trajectories, but with wave function collapse. So in some sense, this theory is a combination of bomb theory and the collapse theories. In this theory, X has also influences on psi, which lead to the collapse of the wave function. So there is a new term as X in the revised Schrödinger equation. Moreover, the probability distribution of X is directly given by the modulus squared of psi. So these two equations will form, as many of you know, will form a collapse model. In my view, I call the series RDM series. So it was proposed in my recent book. I think it's maybe a good combination of the bomb theory and the collapse series. Here is a summary of the series. The first is that the ontology is only particles which undergo random discontinuous motion in our three-dimensional space. So then the primitive ontology is supported in my series. The second is psi is not psi itself is not ontology, I mean it's not a field ontology or something like that. But psi is only a property of the particles. In the literature, it is called a propensity property of the particles. So the modulus square of psi determines the probability of these particles being in every possible group of partitions in space. So I think this provides a better understanding of psi, which lives in the 3n-dimensional space. The third feature of the theory is that psi also undergoes collapse. This is different from bomb theories. I think this is maybe a natural assumption because the particles undergoes random motion in space, and maybe this random motion will have a random influences on psi. So psi will undergo a collapse evolution. So this is, I think in this way, the Born rule maybe has a natural origin. So this is a basic summary of my RDM theory. So I have also proposed a concrete model of the wave function collapse. So this model has a new feature is because it satisfies the principle of conservation of energy. As many of you may know, most of the collapse models violate the principle of the conservation of the energy. So in my model, the energy is conserved. And another feature of the model is that it is based on the RDM picture, based on the picture of the random discontinuous motion of particles. And I also argued that this model can be consistent with the current experiments. So thank you. This is a talk. Thank you.